Okay, so welcome back to day 2 of section 5.2. We're talking about the definite integral, so let's remember what the definition was. It was from a to b f of x dx equals the limit as n goes to infinity of the sum from I equals 1 to n f of xi star delta x, where xi star are our sample points we're choosing on our intervals. Now, remember that this thing's going to exist if we have a continuous function or one that only has finitely many, so that is not infinitely many, jump discontinuities. So when we're looking at this, as long as basically you don't have an asymptote, this thing will exist. The trouble is just figuring out what it is. So I'd like to just work through some examples. Because working through these examples of what we're going to call the limit definition will help both on the homework and on the exam in trying to understand this whole summation notation. Okay, so the first step, if I ask you to evaluate something like evaluate from 1 to 5, 4 minus 2x dx. Okay. If I ask you to use the limit definition here, our first step of business might be, well, what is this sum? I equals 1 to n f of xi star delta x. Well, first it might help to see what delta x is. Well, it's going to be 5 minus 1 over n. Now, where am I getting that? Well, I'm looking at these numbers, often called the limits of integration. And that's where the 5 and the 1 come from. And I get 4 over n for my widths. So then I can split up my subintervals. It starts at 1 plus 4 over n, 1 plus 4 over n, to 1 plus 4 over n times 2. And this continues all the way to 1 plus 4 over n times n minus 1. And then with the last endpoint of being my 5, which is the same as 1 plus 4 over n times n. Okay, so that's my intervals. What am I going to choose for my test points? Well, personally, I would suggest, when using the limit definitions, to choose the right test points, because they tend to work out nicely. So my xi star is going to be 1 plus 4 over n times I. And to see that, you could say, well, x1 star is 1 plus 4 over n. x2 star, we see, is 1 plus 4 over n times 2. x3 star is 1 plus 4 over n times 3. And you start to see a pattern, giving us the most general one. Okay, so let's go back to our sum. This sum is going to be equal to I equals 1 to n of what? Well, f is 4 minus 2x, so this is going to be 4 minus 2, 1 plus 4 over ni. times delta x. Well, my delta x is 4 over n. And I can distribute everything. So it'll be 4 minus 2 minus 8 over ni times 4 over n. And let's clear some space. Or, once we simplify this a little bit more, you get 2 minus 8 over ni times 4 over n. And we can start to use our rules we know. Well, this is going to be 8 over n minus 8 times 4 is 32 over n squared I. And we can use our rule that lets us split it up. I equals 1 to n of 8 over n minus I equals 1 to n of 32 over n squared I. On the second term, 32 over n squared doesn't contain an I, so it's counted as a constant. So we can pull it out. And look at that. It looks like that we have this sum, which is we have a rule for, and this sum, which we have a rule for. So we can look at what is that thing. Well, what we get is this is going to be 8 over n times n minus 32 over n squared times n minus 1 over 2. And we can simplify this a little bit more. Into 8 minus, well, this will be 16 n squared minus 16 over n squared, or 16n, or 8 minus 16 is negative 8, and then plus 16 over n. So that's pretty simplified. So then, to find this integral, what we do is we take this limit. As n goes to infinity, because we know the sum is equal to negative 8 plus 16 over n, that is what we're taking the limit of. Well, the first term is negative 8 plus second term, as n goes to infinity, 16 over n goes to 0, so we get negative 8 as our term. Okay, so if there's any questions with that example, just remember you can always comment or message me on Canvas. But we will move on to a little bit more complicated example. So using the limit definition, because that's all we know how to evaluate currently with the integral. Let's look at this particular one. That's a little bit harder. Negative 2 to 0 of x squared plus x. dx. Well, you want to start out with, so we're going to be evaluating the sum I equals 1 to n f of xi star delta x, where f of x is our function x squared plus x. What is delta x? Well, it's going to be 0 minus negative 2 over n, or 2 over n. Okay, so then we can make our intervals starting at negative 2 plus 2 over n, negative 2 plus 2 over n, negative 2 plus 2 over n times 2, and repeat, and we're doing the same rule that we did last time, where we'll choose the right endpoints and these sample points will be negative 2 plus 2 over n I. For the exact same reason we did it last time. You can check out the details yourself. Okay, so then this sum we want to evaluate. Well, that's going to be I equals 1 to n of negative 2 plus 2 over n I quantity squared plus negative 2 plus 2 over n I. And that's all being multiplied by our little width we have of 2 over n. Okay, so I can expand that squared term. What do I get? I'll get 4 minus 8 over n I plus 4 over n squared I squared. And then you still have the minus 2 plus 2 over n I times 2 over n. What is this thing going to be? Well, we can combine like terms. You'll get 2 minus 6 over n I plus 4 over n squared I squared times 2 over n. Okay. Let's clear some space. We can multiply that 2 over n term on the inside. Or sorry, it shouldn't be 8 for the second term. It should be 12 over n I. And then plus 8 over n squared I squared. And so we just need to come up with a nicer formula for that sum. Okay, so we're going to use what we know about our formulas for summation. Well, we can split this up. And then for the second and third term, we have a constant. 12 over n is constant because it doesn't have an I for the second term. And 8 over n squared is constant because it doesn't have an I for the third term. And we can use our summation formulas. And so what do we get? Well, it's 4 over n times n minus 12 over n times n minus 1 over 2 plus 8 over n squared times what? N. N plus 1 to n plus 1 over 6. And we can simplify this even further. Just do some algebra at this point. What do we get? We get 4 minus 12 n minus 1 over 2 plus 8 n plus 1 to n plus 1 over 6n. Or I apologize. I made a little mistake back here. These n terms should actually be you should have an n squared for these, and you should have an n cubed over here. Apologize. So then you'll have 2n and 6n squared. And we're going to leave it like that for now. Okay, so what's going to happen when we take the limit as n goes to infinity? Because that's what negative 2 to 0 x squared plus x dx is the limit as n goes to infinity of that function. It's being a little cut off right now, but to take that limit, well, the first term is just going to be 4, and then the other terms, you could use L'Hopital's rule. But in reality, what it's going to be is the ratio of the coefficients of the highest degree, meaning when you multiply this out, you'll get 12n minus 12. So the limit as n goes to infinity is 12 over 2, looking at the highest degree powers, which is n. And then plus, when you multiply this thing out, you'll get, there will be a 16 n squared plus some other terms of lower power, something n plus something, all over 6n squared. So as n goes to infinity, what do we get? And this is still a limit for this one. This is going to be 4 minus 6 plus 16 over 6, or 8/3. And you can put that in calculator, and that's just going to be 2/3. So the area under the curve from negative 2 to 0 of x squared plus x is 2/3. Now, this seems like a lot of work that we're going through to get the area, but in the next section, we're going to be talking about this theorem that we have, that it's going to allow us to instead of going to this limit definition, to really, with ease, compute the integrals a lot easier using something that we already know how to do. So I will see you all for next section, section 5.3.